So I will talk about barycenters of points in skeleta of polytopes. So I'll first say a bit about polytopes, but I'll just go through some basic definitions very quickly. So we say polytope, or rather d-polytope. This will be some convex hull of some finite subset of RD, but let's say with full dimension, where it spans and we'll say a face, let's say K face. Actually, I will say this being, let's say R D prime for D prime greater than or equal to D. It spans a D dimensional subspace. And a K-face is sets of the form X K-face of P. This will be X in P of the form AX is less than or equal to some B for some A and B. And the K skeleton P is I'll denote this by PK. This is the set of all K faces of P. So if I think about like a square, right? This would be a nice example of P, and I pick out the vertices and I take the convex hull of all that. I get the square, and if I look at the boundary of the square, I get the one skeleton, right? So just the edges all together are the one skeleton, and then the vertices are the zero skeleton. So I want to consider the following statement. I'll use P for predicate. This would be some statement K1 up to Kn. It depends on these parameters. This is the statement for every K1. If we sum all these numbers up, the sum from K1 to Kn, dimensional polytope, P, and every point, little p and big P, there are points, let's say x1 in the K1 skeleton of P up to xn in the Kn skeleton of P, such that the given point P is equal to the barycenter of these points. So this is some logical statement that depends on the parameters K1 through Kn. So I could ask for which parameters is this statement going to be true. So you can think about let's say in the square. So if one example would be P11. Okay, so in this case I'm asking, can I find 2 points on the boundary of a polygon, a convex polygon, such that any convex polygon, such that if I pick any point inside the polygon, I will be able to write that point as the barycenter of some 2 points on the boundary. So in this case, let's say I pick some point in here, and I could start by, if I want to guess where those points might be, I could start by just drawing some line through here, right? But this might not be the barycenter. So how would I tell if this is the barycenter? Well, if I look at this segment, and if I look at this segment, it should be the midpoint of this line, right? So let's say this is one point, and this is my other point on the edge. It should be the midpoint of this line. If my target point P is going to be the barycenter, the average of my 2 points, it will be the midpoint, which means this red length should be equal to this yellow length. So that might not be the case, but I could take this line and I can spin it around, and in the process of spinning it around, whatever value this red one was will have been exchanged with the yellow one, and just by the intermediate value point, at some point spinning around, they have to become equal. So this is a rough sketch of a proof that the statement P11, this is true. And some similar kind of argument to this will tell us the following about when this is true and when this is not true, which I think essentially captures the entire picture. So we have the following statements. If I pick some k, I can make any number of k's and then any number of k plus 1s. This is true for, let's say, and how many of these are, let's say there are, let's say there are r of these, and there are n total, right? So this is true for any parameters k, n, r. Let's say r should be less than n, right? This is the remainder. And the following are false. So
do you require r to be at least equal to 1?
No. Yeah, so that's a good question. Yeah, so these can all be equal. So I can put in here 0. Yeah, okay. I could set r equal to n or r equal to 0. You could make a choice, but usually if I take a remainder when dividing, I would make my remainder 0. So the following is not true. Let's say if I put in k minus 1 and any number of d's, let's say, and then let's say I have n of these again total, right? So here I will set this is false, where here I'll set d equal to nk plus r, and if I put if I require more than n minus r, right? So if I go to here, let's say I have n minus r plus 1, and then I have r let me add a parameter. These will be for a d-polytope. I'll specify what the dimension is. So this is false for again here d is equal to n times k plus r. So here I have r minus 1. Yeah, sorry. Yeah, so overall I have n of these. I have n points which are going to be in the faces, and I pick my dimension to be nk plus r. So these are kind of the boundaries. As long as the dimensions of the faces where I want my points to be differ by at most 1, I can find such points, and if 1 is 1 smaller than the remainder, or than dividing n by k, then I can't do it. And if I require more to be in the smaller dimension face, I can't do it. So this is this is true for d equal to nk plus r, which also means that it's true for smaller k, because you could pick your point to be in some face, and you can always make it a larger polytope. So. Oh yeah, sorry. This will be dimension 2. So in dimension 3, this would be false. You can't write. If you think about it, you would be picking a too low dimension space to even fill the polytope. So one thing I want to point out is some motivation for this. Let's say I like bowling, and I have some very dirty bowling ball. I don't want to wash it at the alley, so I go to wash it in my house, and I say, well, I'll wash it in my washing machine. So I put the bowling ball in the washing machine, and I turn it on, and it spins around very, very quickly. I think it would rapidly destroy my washing machine. So the point of this is that if you have some you have some machine, and let's say your machine is some polytope-like thing with some chassis around the outside, and you want to make your machine kind of be spinning around. Well, wherever it's spinning, whatever axis it's spinning around, you want the center of mass to be somewhere on that axis. So how could you do that? Well, you could try to attach some counterweights around the outside of the machine. So maybe you can put some weight here, and you could put some weight, and let's say these weights are much heavier than the machine, and let's say here and here, so that the barycenter of these points will be some designated target point that you want to rotate the machine around. So this was a kind of an engineering. Oh wait, I put these in this face. Let me pick this point. Let's say. All right. So I want to describe now. I go through first why this is true when r is 0. So for the case of r is 0, requires some a little bit of a topological argument. So I'll use the following statement, which I will it'll have several terms that I should describe, but so if let's say X is a d-1 connected space. So what does this mean? This means that if I have some f from S d-1 to X, then there exists some f tilde from, so this is a sphere from a disk, or else I'll say B, the ball inside the sphere to x such that let's say I'll change this to a k, such that the restriction to the boundary of the ball is equal to f. And this is for all k less than or equal to d minus 1. So if you think about, for example, 0 connected, well, in this case, I want to pick a sphere of size at most, of dimension at most 0. So I can only pick a 0 sphere, which is a pair of points. Then I should be able to extend my pair of points by some one-dimensional ball. I can find a path between them. So 0 connected is just is path connected. And 1 connected, this is simply connected. Okay, so I have this. I have some connected space, and if I have, let's say, and I have a group action. G is a group action on X and Rn, Rd, and let's say it's free. So this, what does this mean? This means that I have a map from, let's say, G times X to X, and it should be continuous, and GH of some X is equal to G of H of X. Right, so applying the action works well with composition, essentially. And this is free on X and RD. No, sorry. Free on RD with 0 removed. And what this means is that if I have some V and G, then if G of V is equal to V, then either V is 0 or G is the identity. So an example of, I'll make some example. Suppose I have the disk. So in disk, I look in the disk at rotation by let's say 2 pi over 3, and let's say minus 2 pi over 3, and the identity. This will be my group. So this is not free in the disk, because if I rotate if I take a 1/3 rotation around the disk, this point will remain fixed. Right? So this action is not free on the disk, but it is free on. This is not free on the disk. But it is free on the disk with 0 removed, because 0 is the only point where I get some problem, some fixed point of a non-trivial action. So and if I have some, let's say I have some phi from x to rd such that, and this is also continuous, so that phi of g of x is equal to g of phi of x, then I know with a bunch of these conditions, I know there is some x, let's say v in Rd such that phi of g is equal to 0. Phi of v is equal to 0. So I know, so as long as I have a function that has this kind of symmetry to it, and the domain is sufficiently connected, somewhere that function has to vanish.
The group action is on X or on RT?
On both. The group action is on both, and that group action has to commute with phi. That's so. This is related to some. This actually is related to vector bundles, and was some reason for me being interested in vector bundles. I think I did this in the wrong order. So how can I use this here? So what this is some kind of tool for showing that something vanishes when you have some kind of symmetry. So I want to measure how far off am I from getting an answer to this problem, and then show that how far I am from getting an answer, a solution vanishes, to show that I have a solution. So I want to define some function phi, which is measuring how far I am from a solution. So I'll take a set of endpoints. So phi, let's let p, this will be some nk polytope. Okay, and then I'll consider, let's let x equal to x1 up to xn in p to the n. So this is something in R n squared k. And so I want to measure how far I am from being a solution, and my way of being a solution is that I'm in the k-skeleton. So I'll let phi of x be the distance. This will go from. So first, let me first. Before I define my distance function, I will restrict to things that have the desired point as the barycenter. So let's let's assume that p is equal to 0 is in my polytope, and this will be the point that I want to be the barycenter. So I'll write some space y, I'll call it w, as the set of x1 through xn such that these sum to 0. Maybe this is and then I'll define phi from Pn intersected with w to r to the n by phi of I of x, this will be the distance of the point xi from the k-skeleton minus the average distance. Let's say j. Okay. And I can check some things, but so let's let Q, if I let Q be the Pn intersected with W, then if I look at, I can check Q of n minus 1, the n minus 1 skeleton, this is n is n minus 2 connected. So this and this map phi, actually it goes to the diagonal, because if I sum up the coordinates, right? If I look at the sum phi I of any x, I always get 0, right? Because here I'm taking the sum of things, in each case subtracting the average. So if I add up a bunch of things where I subtracted the average from each thing, then the average becomes 0. So these sum to 0, which means that actually this is a map to R n minus 1, and I can choose my right. So I'll say this is some R n minus 1 in R n is the diagonal, and here let's let G. This will be the cyclic permutation of the coordinates. So in other words, Z mod n. Then here, if n is a prime, I have that that G is free. Then in that case, G is free on R n minus 1 with 0 removed. And the n minus, since this is sufficiently connected, I have that this function phi has to vanish. Phi must vanish. So at this point, I have some. So what does it mean if phi vanishes? That means that I can find some point in the n minus 1 skeleton of this polytope Q such that the distance to each of these faces is the average distance. So I claim that, in fact, those points will have to be on the K skeleton. I claim that first that at least one of those points has to be on the K skeleton. So let's so this vanishes at some point x in Q n minus 1. Right. So what is the point of, since phi vanishes, since phi of x is equal to 0, what this means is that the dimension of the face, rather the distance of x1 to the K skeleton, is equal to the distance to x2, and so on up to, all of these distances are equal. So, and the other thing I can observe is, suppose, let's suppose that for every I, xi is in xi is not in the K skeleton. So this means that that each xi is in some face of P of dimension K plus 1 or more. Right, so if I add up all of these dimensions, this means that x, this is in a face of P of dimension greater than or equal to n times K plus 1. Right, and now, here this is the nth product of P. Then if I take the n-fold product, I just add up the dimensions of each of the points, right? If I'm in a product space, the product space. But here I intersected with this W, so this means x is in face of Q, which is P to the n intersected with W of dimension at least n times K plus 1 minus, so what was the codimension of W is nk, which is equal to n. Right? Because, so what is, how is W defined? W is defined by each of these points. X is in R nk, right? So if I say that this vector equation is an equation in dimension nk, so if I require this constraint, I'm requiring a constraint in each coordinate. So really, I'm requiring nk constraints, since this is in W is a since xi is in each xi is in R nk. So this has codimension nk, which is this is a contradiction, right? Because now I have my point, which was in a face of dimension n minus 1, now has to be in a face of dimension at least n. So this is a contradiction. So there exists at least one xi in P K, and since all of these distances are equal, I have for all I xi is in pk. So now I have all these points are in a k-face of the polytope. So I want to say a little bit about this kind of topological reasoning and where this comes from. So one way you can see this is by making a vector bundle, which is kind of like a space. So if you want to look at this phi where it vanishes, you want to maybe look at the graph of the function and see where it goes through 0. And the graph of the function is on something like whatever the domain is times the target space, and it's some subset of that. But here it has some kind of symmetry, so you can quotient out by the symmetry, but then it might not be in that product space. It's in a different space, which is kind of like a product space, but not quite a product space. And that kind of space is a vector bundle. And there's something, an Euler characteristic, which is something from topology, but this actually comes from something from graph theory. So where did the name Euler come from? I don't think he came up with this, but there's a certain formula which is f minus e plus n is equal to 2 for planar graphs. And the Euler characteristic of a tangent bundle actually is related to this formula. So I could maybe in the afternoon I might explain that to some people if they're interested, or some people are interested in oriented matroids, so I could explain about this. This was all maybe a bit faster than I had intended, but are there any questions?
Does this in any way recover the two-dimensional proof you just said n=2?
Yeah, in some sense it does, right? Because you can think about, so what is this vanishing telling you? So in the two-dimensional proof, right, we have some line here. We could say, well, I'm going to look at this distance minus the average of these two distances. I'm going to look at this distance minus the average of these two distances. I have this symmetry by an action of swapping these two, which sends something positive to something negative, and this is saying that if you have some symmetric function from the circle to R, that somewhere that function will have to vanish. And this is essentially what was happening in the two-dimensional case. So this vanishing is like using the intermediate value theorem, but where you have more than one dimension. So the intermediate value theorem could be like a one-dimensional version of saying this function has to vanish.
Another question? Yeah, now let's take